Now our next goal is to recast these notions of magnitude or norm and orientation or angle in terms of the so-called standard inner product on R2 and R3. Now this name, standard inner product, may be new, but the thing that we'll be defining is certainly not new. You have seen it before, and you have called it by a much more familiar name. You've called it by the name of the dot product. So let's define it. For the definition, let u and v be two vectors in R2, u with coordinates u1 and u2, and v with coordinates v1 and v2. Then the standard inner product, or what you've called before the dot product of the two vectors u and v, is the following. The notation is we put a dot in between u and v, and the dot product is simply u1 v1 plus u2 v2. So one important thing about this definition, first of all, is that it is a way of taking two vectors, defining some sort of product on the vectors, but the product of the two vectors is not another vector, it's a real number, or a scalar. So a dot product takes two vectors and creates a product which is a scalar. And of course, you've probably seen this dot product for R3 as well. If u and v are two vectors in R3 written as column vectors here, then their dot product is the analogous scalar expression u1 v1 plus u2 v2 plus u3 v3. And of course, this again is a scalar. Two brief remarks that I'll make here. One, if the vector space V is either R2 or R3, then the remark that we just made, the dot product is a map from V cross V to R. And again, V cross V as a set is just the set of all ordered pairs of elements V and W. So the dot product is a way of taking two vectors and multiplying them to get a real number. That's the first remark. The second remark is this, that we can write the dot product as a product of matrices. And to see why this is, remember that the dot product for V and W in R2, for example, is V1 U1 plus V2 U2. But this can be realized as the product of the 1 by 2 row matrix, V1 V2, and the 2 by 1 column matrix, U1 U2. So we took one of the matrices, V, and we wrote it as a row vector, but that's the same thing as taking the transpose of V. So we see that the dot product of V and W can be written as this matrix product, V transpose W. Let's write down just a few examples. First example, V is a vector 1, 4, and W is a vector 2, 2 in R2. Then the dot product of V and W is 1 times 2 plus 4 times 2 equals 8. Second example, V is 1, 2, W is 3, negative 6. Then the dot product of V and W is 1 times 3 plus 2 times negative 6 equals negative 9. One more example. V equals 2, 1, W equals 3, negative 6. Then V dot W is 6 minus 6 equals 0. So this is, how do I say, an illustration of a property of the dot product that you may already be familiar with. Well, two remarks. One, that it seems that we can take the dot product of two non-zero things and get 0. So this is one way that the dot product of vectors differs drastically from the product of real numbers. And the second remark is that the fact that we get 0 has some important geometric significance, and that is that the dot product of two vectors is 0 if and only if those two vectors are orthogonal or perpendicular to one another. We'll collect that as a remark and state several other important remarks right now as well. So our first remark summarizes this orthogonality relation. Let V equal R2 or R3. Everything we're saying is equally true for either of those vector spaces. 1. Suppose V and W are non-zero vectors in V. their dot product is 0 if and only if they are perpendicular. The second property is that the norm or magnitude of the vector v squared is just the dot product of v with itself. The third remark is that if u and v are two vectors separated by an angle theta, as pictured here, then the cosine of that angle can also be written as the dot product of u and v over the norm or magnitude of u times the magnitude of v. And this, in turn, can be rewritten as follows. Since, as we saw above, the magnitude squared is equal to the dot product of v dot v, we can take each of these magnitudes down here and write them as square root of u dot u and the square root of v dot v to obtain this last formula. So, the upshot of observations or remarks 2 and 3 is the following. Let's just focus on this expression and this expression. We said that the geometry of the vectors in R2 and R3, the thing that we had been ignoring, was essentially the magnitude and the orientation of vectors. Those are the things that we had referred to as the geometry. So it appears that that geometry, the magnitude and the direction, is entirely captured by the dot product or the standard inner product. This standard inner product knows in some sense how long a vector is, and it knows what the orientation of two vectors are. Or we can capture these notions exclusively by exploiting the dot product or standard inner product. So this is the sense in which, as I mentioned earlier, the standard inner product encodes the geometry of R2 or R3. We'll conclude here by recording some important properties of the dot product in a theorem. So for this theorem, let v be equal either to R2 or R3. Take three vectors u, v, and w in your vector space V, and let C be a scalar. Then there are four important properties of the dot product that we'll list now. The first, the dot product of any vector with itself is always non-negative. And, furthermore, u dot u is equal to the scalar 0 if and only if u is the 0 vector to begin with. The second property, that u dot v is equal to v dot u, that is, we say that the standard inner product is commutative. The third, that the dot product distributes over vector addition, so u plus v dot w is u dot w plus v dot w. And the fourth and final property, that if we take the vector u and scale and multiply it by c, and then take the dot product with v, well, that's the same as first taking the dot product of u with v, and then scale and multiplying that result by c. I'll just make two comments here. One, we're not proving any of these properties here. The proofs are all standard. You should go through the proofs and make sure that you can do them. The proofs are in your text. We just won't do them here. The second comment is this. I repeat again the fact that the dot product, or standard inner product, appears to encode all of the geometry of R2 and R3, and it satisfies these properties. So in the next section, we'll do what mathematicians often do, and that is to turn these properties into a new definition and to try to abstract this notion of geometry to much more general vector spaces.